So the final term that remains is this term on the right hand side. Okay. So integrating the delta function, and our integral is including the origin over here. That's my s epsilon, right. So what do we expect? -1, right. So this term should just give me a -1. So here there is one small thing that you have to be careful of. If you the way I have written this looks like a 1D delta function, right. So if you did, you could make a mistake here if you did the following. For example, if you wrote this ds as 2 pi r, sorry, not 2 pi r, if you wrote it as r dr d theta and you wrote this as delta r, you might write this as 2 pi into, right. So 2 pi into integral of r delta r dr, right. So don't do it like that, right. So the correct way, I mean so this is wrong. So the correct way to do it would be just think of this as a 2-dimensional delta function, right. So that's delta of x minus x prime. In this case, it's x prime is 0, so it's just x y dx dy, right. It's a 2D delta function, so its integral is just going to be equal to 1. Okay. So that term c is equal to -1. So finally, what all did we have left over here? The first term gave us -4jb, right. So that gave us -4jb. The second term gave us 0, right. And finally over here I have -1, right. So b is equal to 1 by 4j is equal to -j by 4. Okay. And if I put it all together, finally I can write my Green's function as equal to -j by 4 h naught, right. So what I started with here, I had started with 2 terms and I am left with only the second term, right. So h naught of the second kind k r. Okay. So another thing that is easy to get confused by, because we were being a little not very careful with our notation, I have simply written r over here, right. This r, let us just identify where it came from in the differential equation. Okay. So this r came from identifying this wave equation over here with the Bessel's differential equation, correct. So over here, what is our r? It is a scalar because it matches with the x over here, right. There is a 1-to-1 mapping, and that is the r that I maintained everywhere, right. So finally, by the time I come to the expression for Green's function over here, g of r, what is the meaning of this r? It is a scalar, and what is, I mean polar coordinates, so this value is always positive. It's because it's the distance, radial distance, right. So if I want to write this in a more precise way, where g of r vector, r can be anywhere, then how should I modify this? Or just the modulus of r, right. So h naught to k okay. So it's a minor thing to, if you retrace the derivation, you will see why this mod r should be kept over here. Again, depending on which text you look at, you might find instead of h naught 2, you might find h naught 1, and the reason for that would be j plus jy. Yeah, but why would you choose? Why would anyone write the Green's function as h naught 1? Invert is physically not allowed. Invert waves are not physically allowed. But still, you will find some places where in some textbooks you will find the Green's function written as some constant times h naught 1 k r. What is, and it is correct, and why would that be correct and why would this also be correct? So remember, we had, when we wrote our solution to the Bessel's differential equation, I got 2 terms, h naught 1, h naught 2. How did I choose h naught 2? Before I came to outward wave, what did I have to remember? Time convention. I chose e to the plus j omega t. Therefore, h naught 2 was a outgoing wave. But if my time convention is e to the minus j omega t, then it will be h naught 1, because h naught 1 then is the outgoing wave. The wave has to be outgoing. So you have to see in your time convention which one to choose. Again, so this is a common difference between physics texts and electrical engineering texts. Physics people tend to use e to the minus j omega t. Electrical engineers tend to choose plus j omega t. So you should just be aware, because otherwise you will be off everywhere by a minus sign. And in the case of computational electromagnetics, there is a mix of both kind of authors. So it is a genuine possibility of a mix up. Okay. So we are going to stick to the convention of e to the plus j omega t everywhere. That's why we get h naught to kr. Alright. Now what we had done to simplify all our math was that we put the delta function at the origin, right, and that's how we got this simple looking differential equation. Now let's make it general. So let's consider the case where I have my delta function at any location r prime. How will I get back my solution now? I have to remember what we had agreed on, what we will do. Once I have got the solution, all that I have to do is shift the origin. So what will be the final form that I should write? So minus j by 4 h naught 2, that remains, k. Now what do I write? Mod of r minus r prime. Because this is implicitly making r prime the origin and finding out the distance of r from r prime, right. So just arguing this physically allows us a lot of simplification. Instead, if you had chosen your location of your delta function to not be the origin and insisted on solving everything, you would have had to keep the theta dependent terms, right. Because if, for example, in this coordinate axis, if my delta function is over here and my observer is over here at theta and r, then obviously the way this source is emitting, there is a theta dependence for this guy over here. So I would not have been able to remove the theta dependent terms. Okay, but finally all that matters is this distance, the distance between the source and the observer. All right. So this is the form of the 2D Green's function that we will use. Now I have mentioned this previously. This is a special function, a Hankel function consisting of Bessel functions, right. The main idea is that these functions are not, you cannot write them in closed form, okay, but that does not mean that we can't numerically see what it looks like. So let us see what this function actually looks like. Okay. So that is what we have over here. So what I am showing you over here, this is your j0 of x, or not x, let me just say r, okay, since I have plotted it in the plane, and this is your y0 of r. Okay. So for example, this is your x axis and this is your y axis. All right. So what am I doing? I am just varying x and y, and at each value of x and y, I am plotting this function. Okay. It is a real value, j0 is a real valued function, it has a value, finite value everywhere. So you can see the maxima of this function is happening where? Origin, right, that is the maxima, it is yellow colored, yellow shaded over here, and it begins to decay, okay, as you go away from it, just like a wave. For y0, what is the only difference? Notice this, right, it is plunging to minus infinity at 0, at the origin, right, and again it is like a wave, but it is decaying as I go away from it. Okay. In MATLAB, it is very simple to generate this. So you use your command called mesh grid to generate a grid of xy points, and you evaluate the radial distance. This is element wise operation, and just find out your Bessel j. So they have Bessel j, Bessel y, and so on. That is how you generate these different things, and the surface plot is what you will use to plot this 3D function. Okay. Now just out of curiosity, have you seen something like this in real life? Huh? Ripples where in a pond, or even closer to home, when you have a bath, you put water in your bucket, you see ripples like this, right, on the surface of the water, right. Actually, if you look at the differential equation for the water surface, it turns out to be the same Bessel's differential equation. So the solution is Bessel's function, and if you had to choose between j0 and y0 for water on the surface, what would you choose? j0, right, because physically y0 does not make sense since it is going to minus infinity, right. So from today, whenever you have a bath, you will remember Bessel's functions, right? Because they are there everywhere in nature. Wherever there is a 2D kind of a wave problem, so a 2D wave is a Bessel function. So far in sort of high school, whenever anyone said plane wave, what did you do? You said e to the j kx minus omega t. But if I plot the magnitude of this, the amplitude of this is unchanged. It's a wave that goes off to infinity, it never decays. So even though it's the simplest kind of wave, it's the most unphysical kind of wave. This, on the other hand, these are 2D waves, which physically you can see that they, as you go far away from the center, they begin to decay off, which is what we expect. Okay, and subsequently we will come to 3D waves also. Okay, any questions about this? Okay, so you got a physical idea of what's happening. The waves that satisfy our differential equation are just a linear combination of J naught and Y naught. And why did we choose that linear combination? Because it gave us a certain physical meaning of outgoing waves. Okay, so that's what we had.